In the next section of the course, we're going to be exploring the hypothesis testing framework for answering our research questions. Let's illustrate some of the concepts in the hypothesis testing framework by returning to an example that we discussed a couple weeks ago. In this example, we were asking whether there's a relationship between an employee's gender and the likelihood that that employee will be promoted. In this experiment, researchers sent out 48 personnel files to 48 different personnel managers, supervisors, and asked those supervisors to make a decision about whether the person in that file should be promoted. The only difference in these personnel files was the gender of the employee. And we found that of the male applicants, or the male employees, 21 of them were promoted and 3 of them were not promoted, per the decisions of those supervisors, and of the female employees, 14 were promoted and 10 were not promoted. So the probability for men of promotion was 21 over 24, or about 0.88, 88%, and the probability for women was 14 over 24, or 0.58. So we noted that there simply being a difference in these proportions does not prove that there's a relationship between gender and the likelihood of promotion. There are a couple of possible explanations. One of them is that promotion and gender are not related to one another, and the difference in these proportions is just due to chance rather than any systematic difference in the promotion rate for men and the promotion rate for women. This is going to be what we call our null hypothesis, that there is no relationship between these two variables, gender and promotion. Our research question asks, is there a relationship between these two variables? And the null hypothesis takes the skeptical approach and then hypothesizes that there isn't any relationship of the kind that we're looking for. The other possible explanation is that promotion and gender are related to one another. They're dependent on one another, and that the differences in the promotion rate for men and the promotion rate for women is not due to random chance, it's due to an actual relationship, in this case, gender discrimination. This is the alternative hypothesis. It represents the relationship that we are testing, in this case, the relationship between gender and promotion rates. So this is the hypothesis testing framework. We have a null hypothesis representing a status quo starting assumption that says that there's no difference or no relationship or something, sort of hypothesizes that we're not going to see this relationship that we're testing for. And then the alternative hypothesis represents our research question. So we have these hypotheses representing different conclusions that we could come to about our research question, and then we are going to collect data and we're going to analyze that data and see which of these hypotheses it matches up best with. So we do the hypothesis test under the assumption that the null hypothesis is true. That is, under the assumption that the relationship that we're looking for isn't there. And then we're going to use methods based on the central limit theorem to evaluate whether the null hypothesis is a good explanation of the data or whether we should reject the null hypothesis in favor of the alternative hypothesis. So if the test results tell us that the data do not provide convincing evidence for our alternative hypothesis, we are going to fail to reject the null hypothesis. Now, you should note that we don't accept the null hypothesis, we just fail to reject it. We have the starting assumption and we see if we have evidence to move away from that assumption or not. If the data do provide evidence for our alternative hypothesis, then we can reject the null hypothesis. So that setup might be a little bit confusing. So we're going to take an extended look at an example to illustrate the hypothesis testing framework. So imagine that you are interested in this large box full of tickets and each ticket has a number printed on it. And what you want to know is what the average of all the numbers on those tickets in the box is. You consult an expert who tells you that the average is 50, but you're not entirely sure if you can trust this estimate, so you want to do a test of your own. You don't have the time or the resources to look at every single ticket in this box, so what you're going to do is take a random sample of 500. And you find that the average of those 500 tickets is 48, and the standard deviation you find of that sample of draws is 15.3. So you go back and talk to the expert and you say, hey, I found an average of 48. And the expert tells you that this average is pretty close to her estimate of 50. And so your experiment is evidence that she's right, that the average of the tickets in the box is 50. Is that true? So our research question is asking about the mean of the values on all of the tickets in this large box that we're looking at. So our parameter of interest is the mean in this entire population of tickets. There are two possible reasons for our finding of a sample average of 48 rather than 50. The first possibility is that the real population mean is different from 50, and that the sample mean that we found in our particular sample is a reflection of the real population mean, and the reason it's not as close to 50 is because 50 isn't the actual population mean. The other possibility is that the true population mean in the box is 50, just like our expert suggested, and that we just happened to draw a random sample with a sample mean that is different from the population mean. So our null hypothesis, our sort of status quo hypothesis, is just going with the assumption that the researcher has given us, that the average in the box is 50. And our alternative hypothesis, what we're testing, is whether the average in the box is actually different from 50. We're going to use our sample data to test that hypothesis. So notationally, h sub 0 is that the mean, mu, is equal to 50, and h sub a, the alternative hypothesis, is that the mean is less than 50. So the expert that you talk to is supporting the null hypothesis, this idea that the average number of all the tickets in the box is 50. And her argument is that the reason that your sample mean is different from the real population mean is just due to the luck of the draw, a random sampling error. But you suspect that because you took such a large sample, because you looked at 500 tickets, that the average in the box is actually smaller than 50. So how do you know if what you found, a sample mean of 48, actually gives you information that could lead you to conclude that the population mean in the box is different from 50? That's what we're going to talk about next. So to adjudicate between our two hypotheses, we're going to calculate a test statistic, which measures the difference between our data and what we expect under the null hypothesis. In particular, we're going to find how many standard errors away the sample mean is from the null hypothesis mean. So this is a z-statistic that measures how many standard errors away a value is from a mean. We talked about this a bit in an earlier lecture. So one way to express the formula for the z-statistic is the observed value minus the expected value divided by the standard error. So in this case, under the null hypothesis, we expect to find a mean of 50 if the population mean truly is 50, but we observed a mean of 48. So observed is 48 minus expected, 50, divided by a standard error, which we'll calculate in a minute. Another way of expressing this is just with the mean values that we're considering for this particular research question. So x bar, the sample mean, minus mu, the expected population mean, divided by the standard error. In earlier examples, we've used a formula for the standard error that is the standard error equal to the standard deviation divided by the square root of n, the square root of the sample size. Depending on your research question, you might have to use a slightly different standard error formula. So in this case, we are looking at the sum and then the division of a whole bunch of draws from a box of numbers. And for mathematical reasons that I'm not really interested in getting into in this lecture, we're going to use a slightly different standard error formula to find the standard error in this particular case. So we found a standard deviation in our sample of 15.3. That's the standard deviation of all of the observations that we took out from the box of tickets that we were looking at. So we're going to transform this. The square root law says that to find the standard error for a sum of draws, which is the first step of taking a mean of draws, is to take the sum and then to divide it. So to find the standard error for the sum of draws, we multiply the square root of n, so the square root of 500, by the standard deviation of the sample. So the square root of 500 times 15.3, and that's equal to 342, the standard error for the sum. To find the standard error for the mean, we're just going to divide by n. So divide 342 by 500, and we find a standard error for the mean of 0.7. So let's continue calculating our z-statistic. We are going to take our test value, x bar, 48, minus our hypothesized mean, our expected mean of a sample if the population mean is actually 50, and then we're going to divide that by our standard error of 0.7. So 48 minus 50 divided by 0.7 is approximately negative 2.86. So the value that we observed, the sample mean of 48, is almost 3 standard deviations below our expected mean of 50. So the chance of getting a sample mean 2.86 standard errors below the expected value is about 1 in 500. It's very unlikely. So if the null hypothesis is true, the real population mean is 50, so we expect a random sample that we draw to have a mean of 50. It would be extremely unlikely, if the sample mean really is 50, to draw a sample that has a mean of 48. I generated this graph in R to illustrate this concept a little bit further. So the central limit theorem tells us that the sampling distribution of sample means is going to be approximately normal if we take samples of sufficiently large sizes and our samples are random. So this is a normal distribution centered on the mean that's hypothesized in our null hypothesis, 50, and with a standard deviation equal to the standard error that we just calculated, 0.7. So with this normal distribution, we can find where the test value 48 is in this normal distribution representing the distribution under the null hypothesis and see how unusual that value of 48 is in this particular distribution. So R tells me exactly the same z-score that I found in the calculation procedure that we just did, and shows me that it's extremely unlikely, a probability of 0.002, that we would observe this sample mean in a random draw from a distribution like this. So we just calculated this z-statistic, and we used it to give us information about how unusual it would be to observe our sample mean of 48 if the population mean is actually 50. So we found a p-value. A p-value of a test is the chance of getting a test statistic as extreme or more extreme than the one that we observed, assuming that the null hypothesis is true. So conceptually, if the null hypothesis is true, how likely is it that we would have observed the data that we observed? So we can use R or a z-table like we used in a previous example looking at normal distributions in another lecture. We can use either of those to find the p-value for our particular statistic. So if you look in a z-table for the value negative 2.86, you'll find that that corresponds to a probability, a p-value, of about 0.002. You can also do this in R. We use the p-value that we find to come to a conclusion about our research question. If we find a low p-value, what we conclude is that it would be unlikely to observe our data if the null hypothesis was true. So the probability of observing the data that we observed under the null hypothesis assumptions would be very low. So if we find a low p-value, we can use that information to reject the null hypothesis. On the other hand, if the p-value is high, what that tells us is that there's a reasonably high probability that we would observe what we observed under the null hypothesis. So the null hypothesis explains the data that we observed just fine. If we find this, then we don't have any reason to reject the null hypothesis. We fail to reject the null, and we don't accept the alternative hypothesis. So how do we decide if a p-value is low or if it's high? Well, what we do is we set a significance level. A notation for the significance level is this letter alpha. And the significance level is a cutoff value. Probabilities below the significance cutoff are low, and we use those to conclude that we should reject the null hypothesis. and probabilities above that cutoff are high, and we conclude that we shouldn't reject the null hypothesis. So a common significance level is an alpha of 0.05. So if we observe a p-value less than 0.05, we reject the null hypothesis in favor of the alternative hypothesis, and if it's higher than 0.05, we just go ahead and stick with the null. So what does all this tell us about the example that we've been looking at? So in this example, our null hypothesis was that the mean of the tickets in the box was 50, and we took a sample of 500 tickets out of that box and found a mean of the numbers on those tickets of 48. We calculated that the p-value was 0.002. So this p-value is very low, and it's far below this alpha of 0.05 conventional threshold for determining whether we reject or fail to reject the null hypothesis. So what we find is that it would be extremely unlikely, if the mean of the tickets in the box was 50, to observe a sample of 500 with a mean of 48. That would be very unlikely to happen. So we're really confident in concluding that the expert that we consulted is wrong. The mean of the tickets in the box is lower than 50. That's almost certainly true, because it would be extremely unlikely for the mean to be 50 and us to observe what we observed. So we reject the null hypothesis. As with all statistical tests, there are some conditions that need to be met for the test to be able to be performed validly. So, the hypothesis testing approach rests really fundamentally on the central limit theorem, and the idea that the sampling distribution of sample means is approximately normal under particular conditions. So, the conditions that we need for the central limit theorem are also conditions that we need to do hypothesis tests. And those are that the observations in the sample are independent of one another. A good way to ensure that that's true is to do a random sample. So like we did with the tickets in our box, we took a random sample of those tickets. The sample size should be less than 10% of the population. And if the population distribution is skewed, we should take a sufficiently large sample size. So let's test your understanding with one more example. A poll by the National Sleep Foundation finds that college students average about 7 hours of sleep per night. A sample of 169 college students in an introductory statistics class shows that they get an average of 6.88 hours of sleep per night, and that sample standard deviation is 0.94 hours. So, if we assume that this is a random and representative sample of all college students, which might not be the case, but let's just assume it, a hypothesis test is conducted to evaluate if college students on average sleep less than 7 hours per night. And when we do this hypothesis test, we find a p-value of 0.0485. So, which of these following options is correct? Go ahead and pause the video, read through these options, and see what you think. So our null hypothesis is that college students get 7 hours of sleep per night. Our alternative hypothesis is that college students get less than 7 hours of sleep per night. And we use the data from our sample and this information that we have about the p-value of the hypothesis test to evaluate this. So we find a p-value of 0.0485, which is less than our traditional cutoff of 0.05. So we're going to conclude that college students do sleep less than 7 hours on average, and we're going to reject the null hypothesis. So the research question that we were just examining asks whether college students get less than 7 hours of sleep per night. So we're asking particularly about the direction of the difference in what we find from the mean. So in this case, particularly less than 7. That's a one-tailed hypothesis test. If we changed the wording of our alternative hypothesis and instead we wanted to know whether the data provide evidence that college students get something other than 7 hours of sleep per night, whether they get less than 7 hours or more than 7 hours of sleep per night, then we're going to be doing a two-tailed hypothesis test. So this has some implications for the p-value that we find in our hypothesis test. So if we are taking into account values at both extremes of the distribution, then values that are at the extreme low end of the distribution or values at the extreme high end of the distribution could be evidence to reject the null hypothesis. So if we're doing a two-tailed hypothesis test, our p-value is going to be greater. So with a one-tailed hypothesis test, if you observe a value that is 2 standard errors below the mean, and you have a directional hypothesis that is about values below the mean, then you take a look at that cutoff of the value that you found, that's 2 standard errors below the mean, and think about the area under the curve that is that far away from the mean and less. But if you don't have a directional hypothesis, if you are doing a two-tailed hypothesis test, then what you would do is you would look for the area below that cutoff, 2 standard deviations below the mean, and above 2 standard deviations above the mean. You would look at the area under the curve that far away from the mean in both directions. So that's obviously going to be more area under the curve, which is going to make your p-value higher. So that's been our lecture on the hypothesis testing approach. We're going to talk more about hypothesis tests and decision errors in hypothesis tests in the next lecture, so I will see you then.